right, well, good morning, good afternoon, everyone. My name is Erica Podest, and I'm a scientist working on SMAP. And today's webinar will be focused on the applications of remote sensing to soil moisture and ET. And so we have a guest speaker today. Her name is Vanessa Escobar. And Vanessa is the Missions Applications Coordinator for SMAP. And she will give us an overview of some of the applications that are using soil moisture from SMAP. And I'll just leave it up to you, Vanessa. Please take it on.
Great. Thank you. And do you want me to advance my own slides, Erica?
Yes.
Okay, perfect. Well, hello to everybody, and thank you for dialing in. Like Erica said, this is SMAP application, so the uses of soil moisture data, particularly the uses of SMAP data. I started off with a nice image from the International Space Station, just so we have a reminder for this talk on how science is really intended to serve our understanding of the Earth and the millions of people that, science does serve, and the need to communicate the uses of the science and the different ways we have to communicate it. So we do this through a number of our satellite missions, and as Erica mentioned, I belong to applications. So as the applications coordinator for SMAP, my main role is to make sure that the data coming off from SMAP measuring soil moisture is translated in such a way that end users, whether they're sophisticated scientists looking at unique applications in deeper science questions, or if they're commercial users looking to maybe get an edge on their businesses, equally that all users have an understanding of what the impact and also the limitations of some of these data are. So what I'm going to go over for my talk is really intended to be in that breadth and to talk about the uses. I'm going to give you a little bit of a background for NASA Applied Sciences and the mission overview. I know your first session with ARSET really went into SMAP mission, so I'll just touch on a few things, get into applications, and then really get to the crux of what early adopters are, what that program means to applications and the uses of soil moisture. Give you a few samples of SMAP data applications, and then hopefully leave some time for some question and answers and discussion. So so here, and apologies for the low res if it seems fuzzy to some of you. Here you have the Earth science missions and instruments from NASA writ large, and you can see that we have a lot of things, going around in space. And this slide really represents a number of satellites. We have the satellites that are currently in orbit. We have those that are projected to be in orbit, and then those that have follow-on. And if you can see in green in the most outer section, you see SMAP is sitting there with SUMI NPP, Landsat 8, and GPM. And those are our most recently launched decadal survey missions, which have really empowered, being part of the decadal survey, empowers applications and the capabilities for using science and integrating user feedback into mission product design. And that's really what we're going to talk about today. So, the basic question is, why should we measure soil moisture? And soil moisture has really been a limiting factor in a lot of applications, particularly agriculture productivity in all parts around the world. Soil moisture is measured on the ground in data poor regions, and measuring soil moisture from a satellite really gives us an amazing opportunity to have continuous and constant observation globally. So not only can we calibrate it with the existing ground data that we have, especially in data-rich regions like North America, but we can provide perspective to data poor regions and provide a data gap to areas that don't have a lot of ground measurements. Soil moisture has a huge impact on evaporation, and it's just a very important variable when it comes to not just the sensible heat and latent heat, but it also has a huge role in understanding water cycle, carbon cycle, and the energy cycle. So dynamic global vegetation models, flex models, carbon budgets, they all depend on soil moisture and root zone to give more accurate values and answers for their outputs. So when we look at soil moisture, and when we look at microwaves, we want to understand why we are using microwave remote sensing. And there's just a very strong distinction between wet and dry. And you can see in the image we have a wet soil, which is less reflective, and a dry soil, which is more reflective. Now, I'm not going to get into this too much, but when we look at the microwave brightness temperature, the reason we use microwave is that we have a very strong dielectric constant between dry soil and wet soil. Dry soil has a dielectric constant of around 4, and wet soil has a dielectric constant of around 80. So there's a large distinction between the two, and the contrast allows us to understand when something is wet or dry with microwaves. Also with microwaves, you can see through clouds. So when you're having an event, hurricane or rain, we actually have the capability to see through the clouds and be able to tell if if something is wet or dry. So emissivity, for those of you who don't know, is the capability of the soil or any kind of material on the ground to emit energy in terms of thermal radiation. And so when you have a black body and a black object, that's a perfect emitter, and emissivity really stems from there. So when we know the soil dielectric constant, we can use a standard relationship to calculate the soil moisture. SMAP has a very specific incident angle, so we take the look angle, we take the polarization of the radiation and the dielectric constant to give us our brightness temperature, and that's what we use to calculate our soil moisture in the equations for all of the products that you're going to see from SMAP. So, let's see. So then, January of 2015, we were able to satisfy the decadal survey as the first mission to launch for the new decadal survey, and to satisfy the need for measuring soil moisture globally using both passive and active through microwave remote sensing on SMAP. And SMAP would potentially provide a continuing record to soil moisture observations through remote sensing and a follow-on to the European mission known as SMAP, the Soil Moisture Ocean Salinity Mission. But it would also add the high-resolution capabilities by adding radar. So SMAP's unique nature was to have a passive radiometer and an active radar combined on the satellite. Let's see, my next slide for some reason isn't showing. Let me see. Here we go. Okay. So, like I said earlier, SMAP's role is to really help us understand the connection between terrestrial water, the water cycle, what role it plays in agriculture and weather, energy exchange, how that works at the land surface and fluxes, and then really tie that into understanding the carbon cycle. SMAP has very specific scientific goals. Each mission from NASA is required to have very clear scientific objectives, and so SMAP specifically has promised to link water, energy, and carbon through the estimation of global surface water and land fluxes and energy fluxes. Its use of microwave data for soil moisture observations is going to quantify net carbon fluxes in boreal landscapes and reduce the uncertainty of climate model projections. And it's doing that through the use of L-band, which is that microwave frequency that's really going to allow us not just to penetrate through clouds, but to also see deeper into the soil. SMOS has a penetration of about 1 to 3 centimeters using C-band, and by using L-band, we've increased that penetration down to about 5 centimeters. So there's also an applications return, and by using the science, what we mean by applications return is we're going to have a benefit. We're going to have enhanced weather forecasts, and we're going to be able to improve the flood prediction and drought monitoring through the design of SMAP. And what SMAP is doing is it changed its design from what SMOS had originally done, and it has a conical scan, and I have an image of this later on, and a large antenna which has a 1,000-kilometer swath, which has a very ample coverage, which allows us to get global measurements in 2 to 3 days as opposed to longer periods. So definitely an improvement. And so we have SMAP measurement approach which I said we have the radar, which is the L-band that was providing the high resolution and the freeze thaw. The radiometer, also L-band, which is providing the moderate resolution but the high accuracy. And I think you may have covered this on the last webinar you guys had. They both share the same antenna, which gives you that wide scan, the wide swath at 40 degrees. We have a sun-synchronous orbit, and the mission is, technically all missions are designed to operate for 3 years, but we have enough fuel for 5. And if it's anything like MODIS and continues to operate as well as it has been operating, then we do have the capability of seeing beyond 5 years, which is always a bonus. But as many of you know now, on July 7th, the SMAP radar did stop transmitting due to a power supply problem. And the radar subsystem is no longer operable. We are moving forward with the radiometer as it continues to perform above expectations, which is wonderful. And your science that you're going to see is going to come from the radiometer, some of the historical radar data, and then also you'll see improvements on what we're doing with the radiometer and the substitutions for the loss of the radar. So knowing that we had radar, we had a year of data and the radiometer. We do have some lessons learned that we were able to collect from our predecessor SMOS, which is still in operations, and now from SMAP, and we've been able to improve substantially on radio frequency interferences that we learned SMOS had from the design, and we've been able to improve on that from SMAP. SMAP is able to test the high resolution and high accuracy combination using not just L-band, but the radar radiometer combo. And like I said earlier, we have deeper penetration into soils. We also have better sensing over vegetated areas, increasing the amount of vegetation per grid cell that you can have and being able to see through the canopy. And so, let's see, working with SMOS. So working with SMOS, we've not only improved our design, but we're also looking forward to how SMAP applications will move beyond this mission and what we need to do down the road. And the best use of that information really is provided by our users, which we'll talk about here shortly. So just quickly from the satellite perspective, where we sit is we launched in 2015. We have data acquisitions that started in April, so there's plenty of data. There's a year's worth of data from radar, and there's continuous data from the radiometer. Due to the malfunction, we've been looking at ways to enhance the SMAP mission, high resolution promise to the mission, but we do have beta products that are going to be released here in October for enhancement, and that would be of interest to people looking for high resolution in applications. And as far as the validated products from SMAP, those have been available as of April 30th. So all of the information is ready and freely available, and if any of you have used it or plan to use it, applications is one of the components from the mission that is always interested in understanding how you're using the data and what your applications are. So you may have seen this in your previous webinar of the products that were available. These are actually the existing products that we're going to have with the SMAP radar no longer in operations. And we also have enhanced products. And what I mean by that is that there are going to be several research efforts to recover the high resolution capabilities. One of them is enhancing the radiometer, and the other one is ingesting data from Sentinel-1A and 1B. So when we're saying a radiometer image that looks like this from May 15, we will enhance it using specific methodology to look more like this. And you'll actually hear about the details and the algorithms that are going to be applied for this to happen. But this simple enhancement and sharpening of the image itself is opening the doors for a number of our application users, and it's bringing increased value to the research that's going on with SMAP. So all very positive and looking down the road. And then this is just a product suite and a list of what you are going to be provided, and you can just keep this for future discussion. once the enhanced products are out, and those will be publicly released come December for all of you to experiment with and provide some feedback on. So in terms of the enhanced products, they're really, well, they're not already released, but they are meeting the mission requirements, and they will be released in December. We've just recently updated that. And we have a year's worth of products that will be fed into that. So we're very eager to hear how all of this fits. And in terms of where you can find the data quite quickly, you can go to the data centers. NSIDC or the ASF will host this fantastically. Both DACs are interconnected, and they are, if you were looking for products that may sit at ASF, which was usually radar, that are now at NSIDC, you can link to either, and they will direct you to each, so you can find the products seamlessly. The DACs have also worked with applications quite closely to create visualization tools that are helpful to all types of users and to different ways of finding data and making data, just easier to understand and easier to ingest and to apply. And so if you're used to searching geographically, then you can use their visualization map through SMAP data, or you can do a search by product. They have a variety of options, and this has mainly been due to the feedback from the applications community. So the feedback that you provide does apply directly to how SMAP organizes its data and how it distributes its products. And so they have a number of data services. They have a number of tools. You can actually download the product in its native format, which is HDF5, or you can change it on the fly to GeoTIFFs or KMZs, which, depending on what your uses are, might be more beneficial. So that is really enough background on SMAP and the instrument itself. And what I really want to get into now are the applications. And in terms of applications, we have different meanings. And I say applications, and people sometimes think of phone apps, or they think of different type models. And so really, at the end of the day, I think applications mean something totally different than another person. And the caption, as it reads, it's just, I don't think it means what you think it means. And it's so important to make sure that it's defined and defined clearly. Because when we talk about NASA developing science and developing applications, we usually see, or I've been informed, that we have the user community on one side, and then on the other side, we have the developer working vigorously to create fantastic science products that he in his soul really believes is going to solve a problem and answer a question. However, the question from the science data developer and the need from the user community isn't normally bridged. And so what we try to do with applications is really bridge that gap. And how SMAP does this is with the applications program, through feedback mechanisms in the user community, through engagement strategies, and through the early adopter program, where we seek to make data easier to find, more familiar, and easier to use. And when I talk about uses, the outcome of that gap and the use can be that it's just not user-friendly, and that's where we started. HDF5 was not the easiest format and was not the most user-friendly format for people and for SMAP. And we had a violent feedback for how difficult it was for some people to use. And one of the biggest impacts SMAP has had is that it has gone all the way up to the higher leadership in NASA, where KMZs are now an official format for NASA data. And that was due to SMAP early adopter and user community feedback. So really the applications look at the issues from users versus science, and the National Research Council recommended that applications be formally implemented into the mission structure. Like I said earlier, SMAP is the first mission to do this, and it's looking at not just the mandatory incorporation of application into the mission plan, but it's also become a critical component of the mission structure. And the science team relies on the feedback of the community to really understand what is and what is not working in terms of the data, and how can the data be improved. And the fact that we bake it into the mission program has really made a significant difference to how quickly we release different type products and even test it out through our user community, such as the early adopters. So like I said earlier, defining applications is very important. And how we define applications within NASA and within the mission is that applications are an innovative use of the data products, but they also support decision-making activities that have a direct link to a societal benefit. And that's usually the hook and the hardest part to satisfy. It's usually one or the other. You have an application that has a very good scientific value, but to bridge it to the end user who has a societal benefit sample is a challenge. So when we do our applied research, we apply and provide the fundamental knowledge for the data, but we make sure that there's user policy or business management activities incorporated and have a potential to have improvement on the decision structures from the use of that applied research. And the user communities are inclusive. I mean, they go with individuals or groups, public or private sector, and they span global scales of decision making down to local, and we look at national and international organizations and partners as far as the information that we seek to improve upon, or just feedback that we search for. Now, assessing the SMAP community was one of the first things we needed to do, looking at that gap and trying to understand what was SMAP really like. When we first started SMAP applications back in 2009, we had about 200 people interested in using SMAP data. And since then, presently, we have almost 700 people as part of the user community. So in terms of the survey, we conducted a survey in 2012 to really break down the community and understand who was doing what applications were well represented, and were there any gaps in information. And what the results revealed was that there were gaps between research and policy applications, which was expected. There was a high perceived value of soil moisture, but we didn't have quantitative values yet. There was just a perception. And there was an uncertainty as to how the ground observations would really scale to the remote sensing data. So that gave us an avenue of explanation and teaching and education. And then, of course, where to access SMAP-like data. When the satellite hadn't launched yet, we wanted people to use proxies, and we really need to give people direction on where to find it, and even the ground data, how to access that, and give them a hand in that. So was very useful to us was to understand the distribution of users within our community. And what we learned was when we asked responders to first self-identify, we had 98% of them identify as science data users. But when we asked that category to be broken down further, we had a clear break. You can see that the science and research mainly stuck to weather, climate, agriculture, forestry, and water resources. And then another group, another cluster essentially identified under hazards, disasters, floods, and then another category. And the other category is really made up of risk assessments and forest fire, that community. So these categories are grossly underrepresented, and what we wanted to do from the survey was really understand why, because we listed our first action as let's increase communication with hazards, disasters, and floods and fire, but then increasing communication isn't necessarily enough. We really needed to understand why that community was not well represented. And so when we moved into another part of the survey, which involved policymaking, public awareness, and we asked responders to really identify in that category, 80% of the population responded that their involvement was mainly research-driven, and 60% of the respondents conducting research claimed that they were not actively involved, if involved at all, in any policymaking effort. So we found this to be a very important gap because those involved in research feel that they're not involved or connecting to policy bodies, and in order to make these these science products more known to users in hazards and emergency management, it does have to move out of the scientific realm. So the second action that we created for this program was to really facilitate the movement of science into policy, and that's where the translation really kicked off. Through our work in applications for the SMAP mission, we can help move research into the appropriate operational audiences. And that in itself starts to identify what are the limitations, what are the requirements that we have to address, and what are the user needs. Not so much how does science satisfy the community, but how can the community take up science in a world where everyone has limitations. There's resource limitations, there's limitations on time. And so we had to be cognizant of, theoretical limits as well as, realistic limits. And so the applications for SMAP are broad. You've heard about the weather applications, which is one of the core applications for SMAP. We have applications in agriculture productivity, flood management, flood response, and flood preparedness. There's also drought, and that covers everything from agriculture drought to climate drought, and then that also starts to bleed into famine and early warning systems. When you look at early warning, we look at health, and we look at how does health and soil moisture, how do they relate to each other, and how can things like dengue and West Nile virus, benefit? How can soil moisture help those particular models that help us look at the risks of those diseases? How can it help us understand that a little bit better? And then we get into national security. How can our military understand routes of opportunity and prevention from getting stuck and improve mobility by using soil moisture data in areas there that are, lacking in ground observations? And then you, of course, have the less popular applications that people don't naturally think about when you hear the name of the mission, soil moisture, active passive. You don't naturally think of using the soil moisture observations from SMAP or the brightness temperatures from SMAP to look at sea surface winds. And that's actually a study being done by NOAA. Or look at the SMAP observations to understand thicknesses in ice and try to detect the difference between single-year ice and multi-year ice. That is critically important for ships moving through the Arctic and have risk of piercing a hole if they were to strike multi-year ice. And then, of course, we have fires that are critically important and just go without say on the applications and what the value of that would be. And storm damage. You're going to hear, I'm going to give you a sample from one of our early adopters as to, how does SMAP help predict power outages? And those, again, are applications that the mission right off the bat didn't think about when we put together an applications program. But through our communication with early adopters, these were brought to light, and they've turned out to be some of the more exciting applications for the mission. All of them are great, but when you get new discoveries, you can't help but jump up and down, or at least I can't. So and all of this is really brought about by our early adopter program, and our early adopters are really just a subset of the mission user community. They are very specific users. They are volunteers that really link the early adopter. They link the SMAP data to an application, to a benefit of society. And so what we do is we team up a science team member to an early adopter, and through their collective work, they guide and provide feedback on the uses of the product, and the SMAP science team member really benefits from a broader understanding of how it's applied, and some of the sometimes technical and oftentimes less technical uses of the data that they, as a science team member, would not necessarily be aware of. So there's a deeper understanding with the early adopters involved. And now this was embedded into the mission program a couple of years before we launched to get them familiar with format, to get them familiar with the mission product structure, and really get them up to speed with what SMAP data would look like. We gave them proxies, we gave them sample, we gave them CalVal, gave them everything we could to help them, to give them a leg up on the use of SMAP data. And what they've done post-launch is the early adopters have really just projected and pushed forward into multiple applications with the use of SMAP data. So through them and by engaging with them early on, they've accelerated the use and the applications of SMAP. Those originally intended by the project and others, like I said, in sea ice and power outages that we really did not expect to see. And so the early adopters are really distributed worldwide. You can see we have a lot in North America. We are always looking for more partners, even though they wouldn't be early adopters. We would still consider them applied users. And so research in South America, we have some partners in Europe and in Africa. We have a couple in Australia. There's only one shown there, but I believe we have two now. And so this is just a simulated image of the SMAP radar. And I just wanted to show where our distribution of our early adopters were in relation to that. And this is actually the logo of all of our early adopters. So we engage with communities worldwide, and we have over 48, I'm trying to think how many university users. We have 52. We have 52 early adopters at this time. But, university, commercial, you can see John Deere was one of our partners at one point. Lockheed Martin is still an existing partner. We have Google on board. And then we have some of the NASA centers. We have sport over at Marshall. We have a lot of the agriculture groups like NASS, and we have the USGS. And so there's a broad spectrum here, and the goal is really to have research and decision support operations covered nicely. We have software groups like Excelis creating tools. So it's intended to use the observations for science, operations, and decision support tools for the future. And these next slides really just show you just some of the early adopter partners. And like I said, we have the NASA Snow and Ice Center down on the right-hand corner. That's the DAC. And then we have the Short-Term Prediction Research and Transition Group up on the left-hand top left, which is sport. And they're working on assimilating soil moisture observations into real-time, high-resolution land surface models. Whereas the DAC is, it's a user facilitator for improving not just the format, but improving on where you find data and how you access it. So some of the early adopters, as I mentioned earlier, are very actively involved. And what I did was I pulled together just some advocacy quotes, and just to quote exactly what they're doing, and so you understand, from their own perspective. We put together a video some time ago, which you can see at the bottom, and we also have a Journal of Hydrometeorology where most of their papers are submitted, where they're taking soil moisture and what they're doing with it. And for example, the Army is looking at soil moisture and mobility and really understanding not just water security, but soldier safety. And then you have the National Drought Mitigation Center, which is a huge organization, and looking at these data at the higher resolution originally, and now looking at the radiometer to cover the entire country. And so they actually work with analysts, and this is an ongoing system where this is updated on a regular basis. Then you have NOAA looking at soil moisture applications to improve weather forecasts, and then you have NASS, which is really looking at the potential for saving money and looking at soil moisture measurements for agriculture at a county scale. And I'll show you what they're doing here in a couple of slides. We have Columbia University looking at the livelihoods and rural populations. So they're looking at the vulnerability of drought and floods. And then we have commercial companies like AER using SMAP data to look at the details of flooding events, specifically flash floods. And our group up in New York at the City University of New York is looking at water quality. They're working actually with water managers to understand how soil moisture data helps them understand water quality for the city of New York a little better. And again, at the bottom, if you copy down that link, you can both see the video and read the publications of all of the early adopters and get a little bit more background on their stories. Obviously, it can't be covered in a 1-hour webinar. So moving forward, we have various categories that are covered, and we have 5 early adopters looking at weather forecasting, 9 in drought, 7 in flood, 1 in carbon, 3 in national security, which includes Army mobility and sea ice. Excuse me, those are just Army mobility. I broke out sea ice into 5 other early adopters. We have 5 early adopters looking at human health, 11 in agricultural productivity, and then we have 6 creating decision and communication support tools. So if any of you are interested in, again, getting more details on each of these early adopters, I'm more than happy to provide that after the webinar. There's a lot of information here. But again, it's just to emphasize the opportunities that these early adopters give and the relationship that we've had with them pre-launch and now into post-launch, and the process where it's all been new. This is all benchmarking, where by providing them proxy data and sample data, and now by communicating with them on the uses of the information, we're only a year and a half after launch, and we have quantitative results for a lot of their work. And the next few slides are going to give you some examples of the work that the early adopters are doing. And closest to my heart is flooding, so I start with that application since I'm involved in this quite heavily myself with my own research. And flooding is one of these fantastically broad applications where you can apply SMAP data. And SMAP is being used to look at both global flooding and local flooding. And the applications for flooding scale from the reinsurance industry to NOAA to local users, for example, the state of Maryland, where the soil moisture observations are being used to understand how saturated the soil is and what is the risk of flood to a particular area. The reinsurance obviously wants to understand this because there's a difference between insurance, which is your local State Farm and Allstate, and then your reinsurers, and those are the insurance companies that insure the insurance companies. So this is kind of an umbrella. So the reinsurers covers the risk, and it distributes the burden of a storm or of an incident. So for example, when Sandy hit, you had several reinsurance companies share the burden across the membership they have at the highest level, which is through the Lloyd's of London. And so we communicate the benefits of soil moisture to the Lloyd's of London and to the reinsurance. So they have an awareness and an understanding that by using soil moisture, you can put it into modeling. And they use global models that evaluate the soil and look at the saturation levels and then evaluate risk. Their actuaries will evaluate the risk of a particular area and see if a storm would potentially cause losses. And that's not losses of life, but that's losses of property. So they look at it from a monetary standpoint. Also using the SMAP data, you can evaluate the runoff of models, both river floods and precipitation flooding. So evaluating the scenarios, both at a county scale and a state scale, are very important. And we have NOAA doing that. And we also have one of our early adopters, which is known as Storm Center, using a tool that simply layers soil moisture data as a KMZ. It's not evaluating or taking an assessment of the data itself, but using it as a layer for situational awareness. So you have a broad use of the data, whether it's going into assimilating different values, whether it's looking at the evaluation of the soil moisture and assessing a risk and giving you a risk factor, looking at the soil moisture as a tool for situational awareness, flood is an incredibly popular tool for soil moisture and for SMAP. Now, how we've improved the communication and how we seek to improve the communication since the loss of the radar, most of those early adopters that I mentioned were all involved with the high resolution product. The enhancement is going to facilitate a better discussion. The population that is interested in flood unfortunately had to wait a little bit and stall for the radar. But this high resolution image, which is an enhancement from the radiometer, which you see to the left, that is a 9-kilometer enhanced visual image using Backus-Gilbert, and which you'll learn about in the next webinar, and then improving the spatial resolution potentially to about 25 kilometers. That right there opens the door for flooding again, and it really enables the Civil Protection in Italy, Storm Center, Google, the University of New Hampshire, Willis Reinsurance, and the World Food Program all to continue research and applications in flood. And what I was doing just previous to this webinar was a couple of weeks previous to this webinar was working with FEMA and trying to really understand in terms of flood and in terms of SMAP data. There's a decision process and a data timeline where flood managers and risk assessment people within the flood industry use data. And so right now what we're doing in applications is mapping out where does SMAP fit in the decision timeline of flood management, and where does the uncertainty and the accuracy really trade off? How important is timely information versus accurate information? And at what point in the decision process do you start providing information more quickly and start worrying less about the resolution? And so that's actively going on right now, and we're communicating with FEMA and through our early adopters, getting a better understanding as to where SMAP data fit best. And so this is an ongoing learning process. So one of our early adopters in flooding that is enormously advanced is Luca Broca out of Italy. And he is a SMAP in flooding operations in central Italy. And he is now the passive, was interested in radar, and obviously has adapted to the passive to get real-time acquisitions of soil moisture over Italy. And he validates his real-time assessment with ground networks. And this is, directly with the communication of the Civil Protection Group and the flood managers. So he puts the data into a national scale flood warning system, and he looks at flood and he looks at landslide potential and landslide risk. And his real-time assimilation of SMAP data into this operating system feeds into the central Italy decision process. So the validation with ground data based soil moisture observations are something that Luca is very fluent in. He's had 3 publications, which I'm happy to send to anybody who's interested, or provide it to the ARSET hosts. Brock, I'm happy to send it to you and you can share it around. But Luca's use of SMAP data in flood operations in Italy is just really unique. He's simply just waiting on funding, and he will be one of the first users where SMAP is both scientifically, quantitatively valuable, and also societal obvious benefit to the Operation Flood Alert map that he's provided. So he's actually one of our really great examples. Another use of SMAP data in flooding, I mentioned earlier when we were looking at the general applications, is prediction of power outages. And what Steve Queering has done is we were waiting for storms early on, and unfortunately we didn't have any storms for him to look at. So he looked at historical storms, and he applied SMAP data to the field areas where Sandy hit. And what he did was run a scenario, and he used modeled soil moisture, which was calculated, and then he used soil moisture observations from SMAP. And he ran the scenarios, basically a data denial, to understand, had Sandy passed through at that time, and had we used SMAP soil moisture, would we have known, would we have any better information on how many people would have been affected with power outages? And it turns out that we would have learned more people were affected with power outages using soil moisture data than the calculated soil moisture from the models. So our update now is to find out if he was able to apply this algorithm and look at the SMAP data post-Florida storms and find out, how many people were actually affected based on his prediction and the actual outages using SMAP data. So again, ongoing operational research that given our area and the sensitivity we have to power outages and the derechos and everything that we've had out here on the East Coast, I would really love to know if I'm at risk for power outage, because I would plan for a hotel farther away much quicker. Spending 7 to 10 days with no power is never fun. So fantastic research, and like I said, ongoing with Steve Queering and his team. Another application we talked about was drought, and I'm looking at the time, so I'm going to speed up a little bit so we have some time for questions. The USGS is looking at a new soil moisture promise for understanding the drought that's dominated really by grasslands and shrublands. So validation of SMAP soil moisture data and in situ is really being used to estimate high and low levels of drought capabilities and potential. And so what they've done is they have taken a study area, and study areas are dominated by grasslands, and the stars on the charts represent the locations in the U.S. For the U.S. Climate Reference Network, which is soil moisture sites in the U.S. And then the background is a sample image of the average soil moisture for the field summarized. So the validation of the SMAP data versus the observed soil moisture is very much in agreement, and the comparison of the SMAP soil moisture against the in situ made the difference in soil depth. They're shaded, and they are the ones that are actually showing the agreement. And you can see that they correlate both in Texas, the Palestine area, the Austin area, and it just really presents a strong argument for the use of soil moisture in these areas and helping us with drought monitoring. Now, this is obviously going to the USGS. We also have the U.S. Drought Monitor, which is looking at it, different ways of applying and actually using the data given the internal processes. But again, the agreement of the SMAP data with the ground data is just such a strong and valuable argument for using the data operationally. And that really brings us to something supported by USAID called FuseNet, the Famine Early Warning System. Now, FuseNet, their objective is to incorporate remote sensing soil moisture into the Famine Early Warning System. And it's to quantify the benefits of microwave. This is their agreement with us. They want to help us understand the benefits of SMAP data. And really, we're conducting experiments with them to test and assess the impact of SMAP in their area. Right now, what they do is they focus on a precipitation model to see whether or not the soil moisture values that they extract from their model agree with the ground observations. And they also have a very data poor region. So what they're testing is to see, does SMAP agree with their model outputs? And this is actually a very political process. For FuseNet to use information, it's more than just being right or wrong. FuseNet has to be 100% certain of what they put into their drought reports, because it could potentially give false information for famine. And so what they seek to do is seek ways of incorporating data to give a better famine prediction. And because it involves human lives, it requires a lot of assessment and analysis. And so SMAP right now is being introduced, and it is in agreement with what their models are saying. And so now it's a matter of presenting different scenarios and presenting a timeline to the analysts so they are certain and they have a high confidence rate that by using SMAP, no harm comes to anybody through predicting famine. So very much a scientific process in terms of showing the value of SMAP, but also an internal process for making sure that the livelihood of people are not threatened. In Barcelona, we have an early adopter using SMAP for fire risk. She works directly with the Forest Service, And she's integrated their map into her system and applies risk levels, which is exactly how the Forest Service works: low, moderate, high, very high, and extreme. And that is being used out in Barcelona for all of Spain. And quickly, our decision support tools, we have a couple of early adopters that I'll just go over quickly. We have, I mentioned USDA, the crop condition report through NASS, the National Agriculture Statistics Service. And what they've developed, I'll let you guys take a look on the web when you have some time, is an application called Vegscape. What you have online right now is not the full version that they're developing. But what they've done is they've added soil moisture and root zone soil moisture to a tool that actually provides statistics for your soil moisture at different depths by county. And that's really important, not just for the agricultural purpose and your productivity and anything that has to do with agricultural risk, but it also has to do with the state and how states work and the decisions that are made at the county scales, and allowing the county not only to have an understanding of agriculture productivity, agriculture predictions, but also look at the carbon footprint and being able to understand water resource management. So their application of SMAP data really stems beyond that of agriculture. And then you have vehicle mobility, which is Lockheed Martin. The two images you see, you have 4 squares on top and 4 images on the bottom. They're exactly the same. The only difference that you're seeing is that you have a mobility map on top that blacks out the 2 center boxes, and the 2 boxes below, the boxes below that essentially mirror the top. The center boxes have white speckles in them. And what you see in terms of nomenclature at the bottom are the vehicle types. And what it's showing in terms of, in military terms, is a go, no-go opportunity. Where can military vehicles drive given the weight of the vehicle, the strength of the soil, and the moisture content, the saturation of the soil? Without SMAP data, the 2 center blocks on the top row are omitted completely. There's no opportunity for these 2 vehicles, the ATV and the transport truck, to pass through. However, when SMAP data was applied, the ATV and the transport truck did have opportunity for passing through areas. And this is from central Indonesia, but they're looking at areas in Korea and Afghanistan. And obviously, in data poor regions, it's very important to understand where your vehicles may get stuck based on weight and soil strength. So we have 3 groups within DoD working on this, and they've all teamed up to give a better understanding of soil moisture capabilities. And then we have Google creating a tool. They are looking at an Earth Engine platform and using soil moisture as a layer. So when you go to Google Earth Engine, you can click on soil moisture and you'll have soil moisture from SMAP, and it will tell you what the global soil moisture is. They're using the level 2 and level 3 products. And you will get an understanding for the global soil moisture and have that as an information tool moving down the road. Now, all of these early adopters and these applications are really being used to create case studies for the future. And the case studies that we're working on for the next 2 years are really example projects that help quantify the value, both scientific and societally, for SMAP. And we're doing that for the various categories. And so far, we've been able to improve the data services. We've been able to improve our tutorials and hands-on learning. This ARSET webinar is something that we collaborate with ARSET on, and we hope to, help inform people that want more information, give you hands-on opportunities for working with the data where the mission comes to you, and we work with your organization so you can apply SMAP products. We have joint mission product opportunities where we work with other organizations and other missions, like we work with ESA and SMOS, and we work with the carbon monitoring system. We work with ISAT2, who is also looking at early adopters. And then we really take the lessons learned and move it up all the way up to NASA headquarters, so this can be implemented organization-wide. And moving forward, for the new decadal survey in the next 10 years of satellites that you're going to see, you will see applications as a formal program, as a required just process. So early adopters and user feedback will begin at the very start of the mission, which is several years before launch. So your feedback, your contribution, your involvement with NASA missions is actually more important now than ever before, because learning from you, from the outside world and the outside perspective and the very fine-scaled uses is only going to improve how NASA continues to do science. SMAP started the trend, and now it's because of the feedback and the great participation, it's moving forward and continuing. So we always have application events, workshops, webinars, focus sessions to really invite more people to the programs, and I extend that to everybody on the webinar. And really the common theme is relationships. People think it's about science, but it's really about communication and leveraging the capabilities. So this is our team, and I have probably 30 seconds for questions. I apologize. I tried to leave more time.
Thank you very much, Vanessa, for that excellent presentation.